Thank you very much. I assume that was an introduction. My name is Frederick Brian. I'm representing Swegon, a Swedish manufacturer of solutions for all types of HVAC projects. At the heart of our manufacturing of our own products is the actual heat exchanger. So this is what we put a lot of our development into, to be able to have maximum energy recovery, both sensible and latent, to make a total recovery rotor. We start with we say that the formula behind our indoor climate is the hardware, which we manufacture ourselves. We manufacture all our own heat exchangers, our own fans, impellers, and we also have the software. We control all of our own products, not only make them so we can optimize them and make them work together to give the optimized energy recovery. And also we have the knowledge how to put them together and produce them in our workshops. We also guarantee the performance. This is very important that we have Eurovent certification to be able to have a neutral body to guarantee that what we say in our software, in our products, in our leaflets is correct to zero tolerance. We have our own development facilities in each of our factories. This is the development for the fluid dynamics for the impellers, for example. We make the models in our software and then produce a model, test it in our own test houses, and the figures we get from the testing is what we put into our software, which you can download as selection programs. It's not only for the air handling units, but also for the chill beams, which we also manufacture, and diffusers, along with the chilling equipment. We produced all this in a small village in Sweden called Kvänum. It's about 100 kilometers northeast of Gothenburg. And here you can see our test facility just for the air handling units. We produce, as I was saying, all our own software, and then it's certified by Eurovent. In our workshops, we produce the actual air handling units, the rotors, the fans, the impellers, the casing. All these functions are produced to stock. So you can have any of our units up to 4 cubic meters a second off the shelf. So I like to say that we produce a Lego kit for engineers with intelligence. You buy a gold block, and then you add on a blue block for cooling, put the controls in, and it will start up the function. A red block for heating, silver block for sound attenuation. You just add the products together. And you can do all this with our software. Therefore, we look at the heat recovery. And we have the three main types of heat exchanging, with the rotor, as we were saying, for total energy recovery, the plate exchanger for sensible energy recovery, and the runaround coils for sensible energy recovery. You can see this example for a Swedish condition with a gold unit, 3 cubic meters a second, 2 cubic meters a second in this case, where we would normally, in middle Sweden, use 164 kilowatts if we had no heat exchanger. We can already, with a plate exchanger, come down to only requiring 22, but with a gold rotary total energy recovery, we're only using 2 kilowatts. So for our conditions, it's very favorable to have a total rotor recovery. The special part about a rotor, let's say 90% of our production is with rotors. The plate exchanger and the runaround coils we use in certain projects where there may be some contamination. But for clean rooms, we always use single direction. Then you separate the supply and the extract altogether. So you can have no contamination between the supply and the extract air in the unit. Pollution has always been a discussion with rotors, so we put a lot of effort now into the developing a much cleaner rotor. to be able to recover as much latent energy as possible as well as much sensible energy, but also keeping the units clean. The Part L laws now in England, you're allowed to use rotors in hospitals, not in the clean rooms, but in the wards, as long as you have a correctly adjusted purging sector. We'll look what a purging sector is shortly. The basis for our system is the energy we recover is from the room. The people, the lights, the computers, your indoor conditions, in this case we're saying 23 degrees. Being filtered, F7, giving the energy to the rotor, O going out. The outdoor air, this is a Swedish condition, actually -20, coming in, filtered, F7 again, because we want no particles for allergy, from pollen, etc. Taking the energy from the rotor and coming in. And here you see we have a delta T of 43. So 85%, and we're coming up to 16.5 degrees. That's a vast amount of sensible energy recovery, which is ideal for our winter conditions. But if you have a delta T of only 5 degrees, you still have a delta T 28. You're recovering 85% of the delta T. So you will have about 17 degrees. The bigger the delta T, the more we can recover. So we like it colder or hotter and wetter. That's where we make most of our energy recovery. But the patents we use is our turbulent rotor system. It's a better performance, a higher heat to pressure ratio, at higher thermal efficiency, at low velocities. It's very important that we get the energy as quick as possible. And there's less risk for condensation and therefore freezing. These are the three main factors we've been developing in our system. If we look at our economic rotor, the actual lamination size is 2.3 millimeters, whereas a normal rotor for the competition will probably be 1.5 millimeters. We are able to put in that turbulence, this is the patent, into that laminate, which causes the energy to have more time to give the energy to the aluminium. And this is the way which we get a better efficiency. The smaller rotor would have to be wider to get the same amount of surface area, or smaller, as in this case, to give more aluminium. But then you would get more back pressure. So we've been looking at what is the turbulence, what are the advantages, what's favorable, and what's disadvantageous. And testing in our test house so we get better performance at the heat pressure ratio. You can see here with the increased efficiency at the lower velocities. Our maximum velocity is normally about just over 4 meters per second through the rotor. A lot of the competition have to go to even higher velocities to get the energy recovery. We are also looking at the thermal efficiency along the longitudinal distance of the laminate. This is also giving us more advantage at lower velocities. But one of our main reasons in the north and in certain areas where it's very wet and very humid is the distance between the laminate. Because we have a wider distance, we don't get the water bridging, which is the condensation, which is the latent energy, which is what we want to recover for the cooling power. So this way, we are recovering the moisture for the winter, so you don't have to humidify, and you're dehumidifying in the summer, so you don't have to chill to remove the moisture. It's a win-win situation. An important part is the pollution. The purging sector, which, as you see here, air coming from the room with the energy, may be polluted. So as it comes up into the fresh air coming in, we need to remove that by catching it with a purging sector. And this purging sector is what we have to control. And the speed of the purging sector is very important because we need maximum speed for maximum recovery, but that last little piece of contamination may be coming into the airstream. So we have this carry-over control regulation where we can prioritize cleanliness over efficiency by slowing the rotor down to make sure we don't catch that last little piece of contamination, which gives a very little difference in efficiency. To get those last 3% is almost 50% of our rotation speed. So this way is what we've been testing all the time to meet better quality for pollution using a rotor in many places where previously we'd be using a plate exchanger. The minimum efficiency, what we have to do though for the leakage, the internal leakage. With a rotor, we know the seal, which is a brush going against the rotor, will leak. So we make sure it leaks in the right direction. We put a damper with a negative pressure of 20 pascals to extract. So it's always sucking itself clean. First you balance the room, then you balance the unit. This gives you the ability to make sure that any pollution internal in the unit is leaking in the right direction. So you have a pressure measurement. When you're commissioning, you commission the room and then the unit, making sure the purging sector is having no carryover. You secure the airflows. It also works with VAV, DC demand control ventilation. And our results have shown with a neutral body that the internal leakage is less than 0.5%. Now normally on a plate, in the norms have been talking about 3%. So in a lot of cases, this is the unit, not just the plate or just the rotor. It's the whole unit which is much cleaner because it's cleaning itself. Our soaptic rotor, to be able to do this and to make the maximum efficiency, total efficiency, we now have developed our own soaptic rotor, which has a zeolite coating. The advantage here being that the zeolite has an opening of 3 Årström, it's a Swedish measurement, which is 10 to the minus 10 of a meter, very almost nano size. But the molecule of water is at 2.6, so it will go into the reservoir in the zeolite. Whereas, for example, a CO2 molecule is 4. So it won't go in, it will be sucked away in the purging sector. Therefore, we have a much cleaner rotor. A lot of these formaldehydes, other products which you have in your carpets, in your curtains, in your building, will now be cleaned away. So they won't be coming on the return air. But there is always some particles which are smaller than 3. As you see, the water droplet is 2.6. For example, ammonia, 2.9. So just toilets is still in, if I have a large amount of toilets, you take the toilets separately. But situations like hotel rooms, where you're taking the whole of the volume of the air through the bathroom, then the ppm is so small it's not noticeable. Office blocks, where you have maybe 6 or 10 toilets per floor, then it's not noticeable. There's such a small amount of possible moisture coming into the purging zone that is normally taken away. And all our tests have been showing there's no problem building in projects with office blocks and hotels. This enables us to be able to have all the benefits for higher moisture efficiency, higher temperature, less risk of condensation and freezing, and risk for odors is minimized. But the other advantages are that we have a much more energy efficient rotor. Without the exchanger, with just a standard exchanger with only sensible energy recovery, and the soaptic with both latent and sensible, we're talking about over 50% energy recovery. If we put this onto the Molière diagram or your psychometric chart, looking at an example in Venice, where you've got outdoor 35-50, 25-50 in the room, we need 13 degrees to come to our chill beams or comfort units. That would normally cost 155 kilowatts if you have no energy recovery. If you have a plate exchanger, about 55% energy recovery, sensible only, you get 133 kilowatts. But with a soaptic rotor, where you can recover more energy, sensible and latent, you'll only be using 85 kilowatts. And this brings down the size of your chiller. So we're saving on chilling power. This is our big saving. Although we bought a chiller company, they complain we don't sell so many big chillers, but we sell the chiller and the unit together, selling a package. Selling more by selling less. This way, if you put this then into a room, same conditions, a room in Venice, 2 people in an office, 1 of our chill beam or parasol units. You have the 35-50 outdoors, 27-55 after the rotor. But don't look at the relative humidity, you look at the absolute, how many grams of moisture there are in the air. To come down to the 13 degrees, 8.9 grams. Going into the office, you have 14 degrees, maybe some heat transfer in your pipework, but there's no moisture coming in. Using 7 to 12 water for the chilling, but 14 to 17 water, warmer water, for your chill beam units. So the warmer the water for the chip cooling, the lower energy you're using. In the room you have 2 people, half a gram per person is the norm. So you've got 9.9 grams coming out of the room. You would use possibly in a large building 2 cooling circuits to save on the COP for the different chillers. But the main thing is those 5.1 grams which are coming on the rotor are being carried out by the extract air. So here we have a pre-dehumidification. This is the big saving with a soaptic rotor, a total energy rotor. You're saving both sensible energy and latent energy. And it's cleaner, because you're always sucking yourself the unit clean by making a negative pressure going to extract. This is the system we're building into our dry units. Rather than using a fan coil, you use a chill beam where there's no fan, no noise, no maintenance, no filter, no maintenance, and no condensation. It's a dry system, so you have no condensation in the ceiling. That's the big advantage with our system. But also, wintertime, outdoors at -20, there's very little moisture in the air. So we need to recover the moisture in the room and bring that back in again. You see a lot of Swedes use lipstick. It's because of their lips are becoming so dry and everything's dry indoors. So that's why we have to have humidification, sore throats. So the rotary unit itself, up to 85% efficiency and 75% latent energy recovery with stepless control, saving the cooling costs on your chiller and humidifying as well winter time. And always the correct purging sector airflow. This is the developments we've been doing on our rotor, but we've also been developing our plate exchangers. Excuse me. And mainly for the Nordic conditions, but you have -10, I believe, for your calculations for this area. So we want to keep as much energy as possible before you bypass. With a similar condition here, 23 in the room, -20 outdoors, we want to make sure the defrosting is brought into function when necessary. A lot of the time it's so dry indoors with a plate exchanger, it freezes because of the humidity in the building, not outdoors, as it comes to the leading edge. So we're talking at plate exchangers with their dry energy, but also you have the wet energy, which is even more difficult to remove, because as soon as it goes negative and the moisture coming there, you have to bypass to stop it from freezing. So we put a lot of development into our plate with the Rico Frost. This is the hardware. There's a new damper system, much better lower pressure and lower leakage. And also we have the software to look after that function. Normally you would put at -3 degrees open and bypass. But because we have humidity sensors in the system, we can open and bypass when necessary. So rather than by opening at -3, if there's only 25% in the room, you can open at -8. And therefore you're saving energy in those 5 degrees. Ideal for the Nordic countries. So you're bypassing and you're opening one section or another section at a time. So you can steplessly, or with steps, make that bypass open and close to make sure you're losing the minimum amount of energy. This is the start to defrost. Ice water is removed from the frost. Then you start again, switch it over. As it becomes necessary, you can open the second bypass and bypass again. This is the controls built in. This is why we don't only produce our own products, but we control them. So the difference in the standard solution, if you're looking at a situation with 75.2 dry efficiency, and then that's 27 kilowatts, whereas with the heat or the power of the coil, you're only using 19 kilowatts. We're saving those 8 kilowatts. And if the whole of the system, looking at the autumn and spring, which is our main recovery period, you can see, for example, in Stockholm, we would be having a period of about 3 months, whereas in Paris, you have a much longer period to be able to recover. So it depends where you are climate-wise, how you can use the different efficiencies from the rotors. I imagine you're more like our South Sweden than Paris. So with our plate defrost, it's more compact, it's tighter, more effective, and therefore more advantage for recovery. There's still a but. We use our rotors more than our plates for cleaner rooms and smells, because you can still get leakage from supply to extract. The plate may not leak, but the seals around it, to the door and on the door seals, this is where, after a year or two, you might get contamination. So we always recommend a rotor and single direction supply, extract completely separate for clean rooms. I'm not sure how much time I have, because I can go on a little more.
Don't have any more.
How much?
No more.
No more? Okay. I won't talk about the standard recovery then. Okay. I'm not sure if there's any questions, or do you take that separately? Yep.
Okay. One question, please.
I understand that 85% is thermodynamic efficiency.
The 85% sensible energy recovery is 100% supply, 100% extract, according to EN 308.
My question is, how is total efficiency if you calculate electric energy consumption?
Okay, annual, we call that annual energy recovery. Annual, yeah. Then you will be, the 85% will be closer to 92%.